Too many people here for me to treat, sorry. Unless some of you I think are
we need that in fact.
We will have a lab this week.
Because
it'll be short.
Oh yeah.
No, right. So short lab this week. Not exactly sure what it'll be.
need a zero correction.
So that'll be something for me to work on tomorrow.
Is in our first order.
So today we start Unit 4.
This will have a correction and then 3. And then that's where we want is with 17 right there.
This is about power.
So
I don't think I have any other announcements to make. Those of you who I sent to this room last Wednesday, I apologize. The seminar is this week, so this time I'm sure. I double checked the date, so if you're inclined to come to the seminar on Wednesday, by all means, and I'll remind you of that. Any questions on anything before we launch off the Unit 4?
that's the door.
No questions on anything? Everybody feels good? It's relative to the pass band. So always relative to the pass band. All our corrections are relative to the pass band. Yeah.
Could you do this problem if it's from fall 2012?
Alright, so for the second one, yeah, but then
So we have a low pass filter,
I'm on the right track.
stop
From
band,
the alpha, and you plug that into here. You put in resistor values.
60 dB roll off.
Yeah, I could do this. It's just this stuff that confuses me.
Oh,
The first steps.
Omega C equals 10 to
that's
the
basically
8.
it. And there, like, yeah, that's the problem.
Pass band gain. 20 dB. Add omega C minus 3 dB point. And there's a limited collection of resistors. So looking at this, how can we build this circuit? How can we build this circuit? We've actually done this a couple times. Essentially, so we need a second order. We notice it's 60 dB roll off, cutoff frequency at 10 to the 8. 60 dB roll off means what? We have a low pass filter going to a 60 dB slope, or minus 60 dB, and that means we have to pass a triple pole. So triple pole change of minus 60 dB per decade. And so together, this means triple pole, but at the pole, or at omega C, minus 3 dB correction. And so if we normally have a triple pole where all our poles are real, what would our correction be? Minus 9. So can we build this exclusively out of second order filters?
Yes.
Just second order filters?
No.
No. So second order filter to give us a lift, so to speak, and then a first order filter that's going to give us our minus 3 dB. So if we look at this from a box point of view, LPF, first order, LPF, second order. And we need some isolation in there as well. This is going to give us minus 3 dB. That's our spec. So what is the correction at the cutoff frequency here have to be? 0 dB, which implies under damped with a damping ratio of what? Yeah, you're a little slow on that one, but a couple people beat you. But yes, you're right. Does everyone agree? Anyone not sure what I just wrote down?
How do you get the damping ratio?
Because alpha over omega naught, the correction for our second order HPF, LPF, Bode plot at omega naught is defined as 20 log 1 over 2 times the damping ratio, right?
Yeah.
That's the Bode plot itself, so not the Knox filter we're looking at. So for that to be 0 dB, what does the damping ratio have to be? That's 1/2. So that gives us 0 dB when the damping ratio is 1/2. And so and we have a passband gain, which we said passband gain of 20 dB. K in dB equals 20, and so 20 log of K equals K dB. And this is again one we can do by inspection. What's K in this case? So our K gain is 10. K equals 10, which means we need an amplifier with a gain of 10. And so there's all our different parts. We can build this sequentially. We have a low pass filter. It doesn't matter if I use capacitors or inductors. There's an R and a C. Omega C was 10 to the 8, which is on the previous page. And so, I don't know, we can pick some values. We can make that 1K. That makes that 10 to the minus 5. No, it doesn't. 10 to the minus 11. There we go. For argument's sake, or for laziness sake, I put an isolation amplifier in there because I'm going to use an inverting op amp. And this needs to have a gain of 10, so I'll put 10K there and 1K there, which is a gain of minus 10, but there was no specifications with regard to phase. So in terms of the magnitude response, minus 10 and 10 are the same. They both result in a 20 dB gain in the passband. What's that? This is an inverting op amp. So R2 over R1 negative. And then we have a resistor, another inductor, and then across the cap again there's the out. And so again I can pick some values. 1 over LC has to be 10 to the 16. 10 to the minus 5. 10 to the minus 11, there I have the same caps. And that makes R over L in this case. We want that to be 10, which gives us a damping ratio of 1/2. Yeah?
If you see inverting op amp, there's questions about the phase later on, you know, incorporate 180 degrees out of phase.
You would, right, so that results in a phase change of 180 degrees. So you could, essentially, you could plot the phase of this and then shift it by minus 180 with whatever wrapping occurs as a result of that. Essentially, all negative sign does is change, drop everything down by minus 180. Or equivalently plus 180, it's the same. That was very quick, but did you get what you needed?
Yeah.
There's one other thing a couple people asked me about. was the quality factor, which is something I should have brought up just in terms of discussion. It's part of our language as electrical engineers. Q, very complicated formula, 1 over 2 times the damping ratio. Q is the quality factor. Where you see this more often is in underdamped circuits or underdamped resonators, which are essentially effectively underdamped. We actually talk about high Q. That's the language that you would hear. So if you're looking at some sort of circuit, especially a microwave circuit or something like that, an underdamped circuit is a high Q circuit. So if you read some of the literature, this is really what's said. You know, people don't really say strongly underdamped. You might see that. They're equivalent. This is used, not very common. They mean the same thing. So terminology, they're equivalent, but if you want to get into the good electrical engineering parties, you have to say high Q. And it truly is just the inverse of the damping ratio times 2. Any other questions related to the exam? Yeah.
For underdamped bandpass, is it always 0 dB correction at resonant frequency? Unless there's a
It's not a 0 dB correction, it's just 0 dB at the resonant frequency. If we look at H of S equals 2 alpha S over S squared plus 2 alpha S plus omega naught squared. By definition, at resonance, these guys are equal and opposite, and that, which means they sum to 0, we're left with 2 alpha S over 2 alpha S, which is 1, which is 0 on the dB scale. So it doesn't have anything to do with the damping, in this case, actually, underdamped, critically damped, overdamped, they're all 0 dB at resonance. Where we use, I think the question you asked, where we use the underdamping concepts is to find the position of the vertex of our inverted V so we can identify what a straight line approximation is. Is that clear? Everybody okay with that? Any other questions? This is just one more comment on the test. Those of you who arrange things with me will be in my office at the appropriate time. I don't remember who that was, but I'm sure you'll remind me. And don't fall asleep in the next 2 hours. Well, if you do, wake up by 7. I don't think I've ever had anyone do it in circuits, but those of you in high tech, one of your classmates will do it. Don't let it be you. Okay. No more questions with regard to the exam. Everybody's confident? Gonna crush it? Or be crushed? So, we're going to start looking at transformers. And so these are AC components. From a circuit point of view, our transformer looks something like this. There's our transformer. The transformer has a voltage and then a current. So, transformer is a 4-connection device. You've used them extensively in your life. There's probably one on the street outside the building where you live. It's a way of stepping up or stepping down power. There are ideal transformer relationships. The key word here is ideal. And that's V2 equals n times v1. And I haven't defined n yet, I will in just a second. And then I2 equals I1 over n. N is the winding ratio. And if you look up above, a transformer looks suspiciously like an inductor. And that's because a transformer can be considered two inductors somewhat coupled together, or strongly coupled together, I should say. And so one way of making inductors is to take a nice iron core or other high mu, high permeability material, which you'll learn a lot about when you take fields, and wrap copper around it. And so if you crack open your computer, probably not a good thing to do, but somewhere in there, there's a transformer, or you can crack open your power supply. And if you crack that open, look at the transformer, it is a wire wound around most likely some sort of iron core. Probably a doped iron, but not too expensive. And so the winding ratio here, we can say there's N1 and N2 windings. N1 windings on the left, and N2 windings on the right. And the winding ratio is defined as N2 over N1. And I was considering having you wind your own transformers, but I decided that would be tedious. So we won't do that for the lab. Well, most likely not. So there's our physical layout of our transformers. There's so many windings on this side, so many windings on that side. All we're really concerned about is the ratio between the two of those. So this is a key concept, the winding ratio, and then these are arguably boxable characteristics for an ideal transformer. Namely, we're saying the voltage on the right is N times the voltage on the left. N does not have to be greater than 1. So we can characterize things as N greater than 1. This is a step up transistor. A transformer, not transistor. In other words, V2 is greater than V1. N equals 1. Put that aside for a moment. And less than 1 would be, by converse, a step down transformer. In other words, V2 is less than V1, and they're both used. They both have practical applications. There's good reasons to step down, good reasons to step up. N equals 1. V2 equals V1. In terms of maybe Unit 3 concepts, what purpose could this transformer have? Isolation. So V2 equals V1. And this is often called an isolation transformer. And that is a word that will get you into the good, or phrase that will get you into a good engineering party. Isolation transformers are used frequently, especially in power engineering systems. In the EP lab class that I do, we use them in every lab. They are a safety device. One of the things to think about, and this again will be more significant when you get to fields, but a transformer is a DC isolating device. So DC signals do not go through transformers. Transformers are for AC only. So that's one of the methods they give isolation. You keep the grounds separate. So they have separate grounds. You get isolation that way as well, though that can be problematic, so you got to be careful with that type of thing. From a circuit point of view, how do we use them? Well, simple characteristics. We have a source. We have a source side resistance, an RS. We have a transformer, and I'll write this as 1 to n because everything breaks down as 1 to n in some sense. N2 over N1 is equal to N over 1. So it's equivalence. We don't have to worry about the individual windings. We just worry about the winding ratios. And again, I'm lying to you a little bit, and we'll look at that lie in the next class. But for the moment, we're staying with this characteristic. And so the question can be, what's our load side voltage? Or what's our load side current? There are two ways to analyze things. So how do we find VL? Well, there's two approaches. You can do something called referring the primary to the secondary. And so we should define what the primary is and what the secondary is. The primary, the side with the source. And by very sophisticated and complicated reasoning, the secondary is the side without the source, or with the load. So this is the primary, and this is the secondary. So, referring the primary to the secondary, well, equivalently, I'm taking all this, and I want to replace the primary with an equivalent circuit. It seems a little bit familiar. So I want to take all that and replace it with V Thevenin and R Thevenin. And there's our load. And why do we want to do that? Well, that's a nice, easy circuit to analyze. Voltage divider, you can't ask for anything easier than that. This would be our goal. And so this is the equivalent of the primary. So Thevenin hasn't gone away. If you're taking Introduction to Electronics, it's not going to go away next semester either. So, useful tool for remembering. On the flip side, referring the primary to the secondary, there's the equivalent referring the secondary to the primary. So there's two approaches. And in this case, we have our V source, our R source, and now we have an RL equivalent. Which all this is our transformer plus our load. So there are two ways of looking at things. That's just the RL equivalent section. The goal here in either direction is to get rid of the transformer. So we can get rid of the transformer by moving to the source side, or we can get rid of the transformer by moving to the load side. Or in terms of transformer words, moving to the primary, or moving to the secondary. And so we'll actually look at this one a little bit first. What does RL equivalent wind up being? Well, if we think about this, this is still V1, that's V2, we defined that early on, that's I1, and that's I2, right? That was the definition for the ideal transformer. And so RL equivalent in terms of circuit characteristics equals what? Well, fortunately again, Ohm's law has not gone away. So RL equivalent is what in terms of Ohm's law? And this transformer characteristics. And if it helps, I can draw a dashed line on this guy too. So that RL equivalent is equivalent to this. Well, if you think about it, the nodes here and the nodes there have to be the nodes here and the nodes here. That was true when we did any sort of equivalence. So we maintain those nodes. These nodes can't change from our original circuit, or we have not gotten an equivalent load. So if we have these two nodes in terms of this circuit, what's RL equivalent? Ohm's law is our friend. Over I1. V1 over I1. We're replacing all of this with the resistors. So the voltage here to here, that's V1. And the current going into that resistor has to be I1. That's our connection. So on both of those circuits, V1 has to be the same. That's the whole point of equivalence. Does everyone agree with this? I'm not sure. But in terms of, I should throw my RL in there, put my label back in. In terms of V1, well, V1 in terms of the transformer equals what? NV2. So we can write this as NV2, and I1 in terms of ideal transformer characteristics was I2 over N. And we can rewrite this as N squared V2 over I2. Do you agree? What's V2 over I2? N squared R out. So there's our magic trick. So that's got to give us an equivalent relationship. So, looking at the other side, referring the primary to the secondary, essentially I have RL, and I want to replace it with an R Thevenin and a V source, right? I drew that a little bit bigger than I needed to. Well, from this point of view, how do I find these things? So here's our original circuit, RS. What do I need to do to find these circuit characteristics? Well, to find the open circuit, what do I do with the load? So the open circuit, the Thevenin, there's the S. Circuit looks like the source. V open circuit, right? But that's V2. So what's V open circuit? It's V2, and our ideal transformer characteristics give us what?
NV1.
V open circuit gives us N V1. And so part of our circuit then, we can go ahead and label this as N, oops, NV source. So there's our equivalence when we do the transformation from the primary to the secondary. And again, our goal is to get a simple voltage divider circuit and to find R Thevenin. How do we find R Thevenin? Well, how do we find R Thevenin? Going back a few weeks, what do? We short the source, but we have a transformer here. So we have this transformer on the way. What's another way of finding R Thevenin in circuits that we couldn't do by inspection? I haven't done it for. We can apply a test voltage. Yeah, we can find I Norton as well now that we know the Thevenin. So maybe that's something worth looking at. We can apply a test voltage on the secondary side, or to be a little bit more general, we can apply a test voltage on the right side. If we apply a test voltage on the right side becomes what? The primary. So it doesn't matter which side you connect transformers in. It can be a step up or step down transformer by just rotating it. So the winding ratios can change by connecting the primary on either side, one side just being the inverse of the other. And that winds up being our relationship. Actually, it does bring up another question. Someone just brought up. It's a good one to look at. We can look at I Norton. In this case, how would we analyze this to get I Norton? What do we know using our ideal transformer characteristics? What do we know? So we have four properties, I1, I2, there's I1, there's I2, V1, V2. I2 is I Norton. What's I1?
I'm trying to remember how they knew that.
Well, I Norton is I2. What's the relationship between I2 and I1?
It actually comes out to this.
Well, what about V2 and V1?
Is 10.
We don't necessarily know what
Because it's a
I10 is yet.
I'm not sure.
But what's true about V2?
That's going to be
0. It's a short circuit. We just shorted out V2. This is the short circuit test. Short circuit load. This is a real thing we do to characterize transformers. That's 0. And what does that mean about V1? And so in that case, I1 equals what? Well, V1 is 0. This is still V source. That's R source. What's I1? Yes. over our source. Now we can find the Norton time. These are both things that are done with transformers. You can characterize transformers doing both open circuit and short circuit tests. You do that to get more complicated things. So right now we're just treating transformers as ideal inductors that are coupled together. We'll look at this a little bit harder on Thursday. Okay, so I was going to stop there. Usually a short day today, as I said.
And then,
Any final questions before we part ways?
I mean, that's just proving that it's a negative 3 dB. Oh, no, no. Sorry, never mind what I said. That doesn't. I was thinking of this. That has nothing to do with that.